The ghost passing through you right now. You know what's funny? You're sitting there reading this, feeling pretty solid, pretty real, and I hate to break it to you, but most of the universe doesn't even know you exist. Not because you're unimportant, no, no, no. It's because right now, as you breathe, as your heart beats, as the neurons in your skull fire, little electrical sparks that you call thinking something is passing through you. Something we cannot see, something we cannot touch, something that has no idea what an atom is because it refuses to interact with one. It's going through your hand right now, through your chest, through the chair you're sitting on, through the entire earth, like the earth is nothing more than a polite suggestion. We call it dark matter. And here's what should absolutely destroy your sense of reality. It outweighs everything you've ever seen, touched, loved, or known by a factor of 5 to 1. The stars, the planets, you, me, all of us together. We are the minority in this universe. We are the weird ones. And nobody told you how science actually works. It's not what you think. Let me tell you something about the way science works, because I think most people have got it completely backwards. People think science is about certainty. They think a scientist wakes up in the morning, puts on a white coat, stares into a microscope, and says, "Ah, yes, I have confirmed what I already suspected." And then they write it down in a very serious journal, and everyone nods. That is not science. That is bureaucracy with better equipment. Real science, the exciting kind, the kind that makes your hair stand on end at 2 in the morning, real science, is when nature looks you dead in the eye and says, "You are wrong, my friend. Try again." And that's exactly what happened with dark matter. Now, I want to take you back, not to some ancient time, not to the Greeks arguing about fire and water and earth. I want to take you back to the 1930s, a time when physicists thought, more or less, that they had a pretty good handle on things. Not everything. Mind you, we're never that arrogant. Well, some of us are, but the good ones aren't. Fritz Zwicky and the math that nobody believed. There was a man, a Swiss astronomer by the name of Fritz Zwicky. And Fritz Zwicky was, by all accounts, a difficult human being. He called his colleagues spherical bastards, meaning they were bastards no matter which angle you looked at them from. I have some sympathy for that point of view, though I wouldn't phrase it quite that way myself. Zwicky was studying a thing called the coma cluster. Now, a galaxy cluster is exactly what it sounds like, a whole bunch of galaxies hanging around together, gravitationally bound, like a very large, very slow-moving party in the middle of absolute nowhere. The coma cluster has hundreds of galaxies in it, thousands actually. Zwicky was trying to measure the mass of this cluster, and the way you do that, the sensible way, is you look at the galaxies inside it and you add them up. You see how bright they are. Brightness tells you how many stars there are. Stars have mass. You count the stars. You get the mass. Simple, logical, wrong. Here's the other way to measure mass in a cluster. You watch how fast the galaxies are moving. See, gravity is like a leash. If I spin a ball on a string over my head, the faster I spin it, the more tension there has to be in the string to keep it from flying away. Same idea with galaxies in a cluster. The faster they're moving, the stronger gravity has to be to hold them in. And the strength of gravity tells you the mass. Zwicky measured both, and he got 2 wildly different answers. The mass from counting the luminous matter, the stars, the gas, everything you can see was maybe 100 times too small to explain why those galaxies weren't flying away from each other. They were moving far too fast. They should have dispersed. The cluster should have been falling apart, but it wasn't. And Zwicky said, and I love this, because it's the most honest thing a scientist can say. He said there must be Dunkel materie, dark matter, some invisible stuff we can't see, providing the extra gravitational glue. Now, here's what happened next, and this is the part that should embarrass us a little. The scientific community said, "Interesting, Fritz," and then mostly ignored it for 40 years. 40 years. You know why? Because it was too strange. It didn't fit. And human beings, even very smart, human beings with impressive degrees hanging on their walls, human beings have a terrible habit of ignoring what doesn't fit into their picture of the world. We like a tidy universe. We like a universe that behaves. The universe, I'm sorry to tell you, does not care about our preferences. What dark really means in physics. Now, let me explain something fundamental to you, because I think it's important to understand why this discovery is so shocking. The word matter to a physicist means something very specific. It means stuff that has mass, that takes up space, that interacts with other stuff. When I say interacts, I mean it in the technical sense. It responds to forces, electromagnetic force, for instance. Here's the thing about you and me and this planet and every star you've ever looked at in the night sky. We are made of baryonic matter. Baryons, protons, and neutrons, the building blocks of atoms. And atoms interact with light. That's why you can see things. Light bounces off atoms, enters your eye, and your brain says there's a table. The whole system works because matter and light talk to each other. Dark matter doesn't talk to light. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. You can shine the most powerful flashlight in the universe directly at a clump of dark matter, and the light will go right through it, completely unaffected, as if nothing was there. This is not like darkness the way we normally think about it. If I turn off the lights in a room, the room is dark, but the furniture is still there. It's still interacting with light, just there's no source. Dark matter is fundamentally, categorically different. It is not merely unlit, it is unlightable. And here's where it gets even more wonderful and strange. Let's talk about you for a second. You, sitting there, reading these words. You're made of atoms, protons, neutrons, electrons, and all those particles, they interact with each other via electromagnetic force. When you try to pick up a cup, your hand doesn't go through it. Why? Because the electrons in your hand repel the electrons in the cup. It's electromagnetic repulsion all the way down. There's no actual touching at the atomic level. It's all just electrons saying, stay away from me. This is the force that gives the universe its texture. The solidity of things, the ability to hold and be held, it all comes from electromagnetism. Dark matter has none of this. A clump of dark matter passing through you, and one almost certainly is right now as you read this, it doesn't bump into your electrons. It doesn't interact electromagnetically at all. It passes through you the way a ghost passes through a wall in those old stories. Except in this case, the ghost is real and the wall is you. Now, some of you are asking, well, if it can't interact with light, if it can't interact with matter electromagnetically, how do we know it exists at all? Gravity? Gravity is the great equalizer. Every single thing that has mass, everything produces a gravitational field. I don't care if you're a proton, a neutron, a planet, a star, a black hole, or something that refuses to talk to any other force in the universe. If you have mass, you bend space. You pull things toward you. You matter in the literal sense. And this is how we found dark matter. Not by seeing it, but by watching it push and pull on the things we can see. Zwicky saw galaxies moving too fast in their cluster. He felt the gravitational tug of something invisible. And he was right. Vera Rubin and the galaxy that broke everything. But it took a long time, and it took another extraordinary scientist before the world really started to listen. A woman by the name of Vera Rubin, and she did something even more elegant, even more impossible to ignore. She looked at individual galaxies, not clusters, individual spiral galaxies, like our own Milky Way. And she measured the rotation curves. Here's what you'd expect. If all the mass in a galaxy is in the luminous stuff, the stars concentrated mostly in the bright central bulge. As you get farther from the center of the galaxy, the orbital speed of stars should drop. Just like the planets in our solar system, Mercury is screaming around the sun, and Neptune is shuffling along lazily, because the gravitational influence gets weaker as you move out. What Rubin found was that the speed didn't drop flat out there, barely changes. Stars at the edge of the galaxy were moving just as fast as stars closer to the center, which meant there was much more mass than you could see, not just a little more, a lot more. The mass had to be spread out in a giant invisible halo extending well beyond the visible disk of the galaxy. Again and again and again, in galaxy after galaxy, she found the same thing. The universe was not what we thought it was. Now here's the thing I want you to hold in your mind, because we're going to be coming back to it over and over in this discussion. We have never directly detected a single dark matter particle. Not one. Not in all the decades since. Zwicky first raised his hand and said, something is wrong with the math. We know it exists the way you might know someone is standing behind you in a dark room, not because you can see them, but because you can feel the air move, hear the floorboard creak. Notice the slight change in temperature. We know dark matter exists because of its effects on everything around it. Is that terrifying? Is that beautiful? I think it's both. I think it's the most wonderful and humbling thing in science to know that the universe contains something massive, something everywhere, something that is quite literally inside you right now, and we don't know what it is. We don't know what it's made of. We don't know where it came from. We don't know what it does beyond gravity. and it is 5 times more abundant than everything you have ever seen or known or measured in your entire life. 5 times. The stars, the planets, the comets, the gas clouds, the asteroids, the black holes, every atom in your body, every atom in every human who ever lived, every particle in every ocean on every world we've ever imagined, all of that is 1/6 of what's out there. The rest is dark. And the rest is everywhere around you. The cosmic web, the universe's hidden skeleton. Let me ask you a question. What does a galaxy look like? You've seen the pictures, Hubble Space Telescope, all those beautiful photographs, spiraling arms of light, blue-white young stars, reddish old ones, dark lanes of dust, the whole thing spinning majestically in the void. It's one of the most gorgeous images the human race has ever produced. Now let me show you the same galaxy, but with dark matter. Oh wait, I can't, because we can't see it. But here's what we know is there. Around every galaxy surrounding it, extending far beyond its visible edges, there is an enormous sphere of dark matter. We call it a halo, which is a very poetic name for something we've never observed directly. This halo is not flat like the galactic disk. It's roughly spherical. It's diffuse, spread out, not concentrated in the center the way the visible stars are. And it is enormous. Our Milky Way is about 100,000 light years across, if you measure just the visible disk. The dark matter halo, best estimates put it at somewhere between 10 and 20 times that size. Maybe more. We're not entirely sure, and I'll be honest with you about that, because honesty is the bedrock of good science. We're not sure exactly how big it is, or exactly how dense it is at various distances from the center. But it's there, big, heavy, invisible. And here's the thing that should make you think about the universe completely differently. Without that halo, you wouldn't exist. I mean that in a very literal cosmic sense. Go back to the beginning, well, not all the way to the beginning, we'll get to that, but about 100 million years after the Big Bang, the universe is cooling down. It's full of hydrogen and helium, some lithium, almost nothing else. And it's expanding, and it needs to start making structure, needs to start gathering matter together to form the first stars and galaxies. But here's the problem. Ordinary baryonic matter, the kind that will eventually become you, it was stuck in a kind of photon bath. Light and matter were constantly interacting, bouncing off each other. And this radiation pressure prevented matter from clumping. Every time gravity tried to pull matter together, the radiation pushed it back apart. Dark matter doesn't have this problem, because dark matter doesn't interact with light. The radiation bath means nothing to it. While the ordinary matter was being pushed around and smoothed out, the dark matter was quietly, patiently obeying gravity. It started clumping first. It formed the first structures, and then as the universe cooled and matter and radiation finally decoupled, as the universe became transparent for the first time, the ordinary matter fell into the dark matter structures that were already there, like water flowing into pre-dug channels. The dark matter halos were the scaffolding upon which everything we know was built. Galaxies didn't form first and then get surrounded by dark matter. The dark matter structure formed first, and then the galaxies condensed within it. This is called the cosmic web. And it is, in my opinion, one of the most breathtaking ideas in all of modern cosmology. Picture this. If you could somehow step outside the observable universe and look back at the large-scale structure of everything, you wouldn't see a random scattering of galaxies. You would see a web. Enormous filaments of dark matter, hundreds of millions of light years long, with galaxies strung along them like dewdrops on a spider's web. At the intersections of these filaments, where the dark matter is densest, you find galaxy clusters, the most massive gravitationally bound structures in the universe. And between the filaments, vast, empty voids, hundreds of millions of light years across, almost nothing there, because the dark matter web drained them, pulled the matter toward itself, leaving these cosmic deserts behind. We have mapped this web, not the dark matter directly, but the galaxies that trace it. And the match between what our computer simulations of dark matter structure predict and what we actually observe in the sky is extraordinary. It's one of the strongest pieces of evidence we have that our model, as incomplete as it is pointing us towards something real. The bullet cluster, caught red-handed. Now, let me talk to you about something called gravitational lensing, because I think it's the most beautiful demonstration of dark matter's reality. Einstein told us, and I love Einstein for this, it's a genuinely wonderful piece of thinking. Einstein told us that mass curves space-time, not space, space-time. And when light travels through curved space-time, its path bends. It follows the curves, the way a ball bearing follows the curves of a rubber sheet. Now, this means that a massive object, a galaxy cluster, acts as a lens for the light coming from objects behind it. The light bends around the massive object, and depending on the geometry, you can see the background object in multiple places, or stretched into arcs, or smeared into a complete ring, what's called an Einstein ring. Here's the wonderful thing. The amount of bending tells you the mass of the lens. It's a completely independent way to measure mass. And when we do this, when we measure the masses of galaxy clusters using gravitational lensing, we get exactly the same answer as Zwicky got from galaxy velocities. Lots more mass than you can see, 5 times more. The same number coming from a completely different measurement. That's not a coincidence. That's nature telling you that you're doing something right. But there's an even more beautiful demonstration. It's called the bullet cluster. And if you haven't heard of it, you're in for a treat. The bullet cluster is actually 2 galaxy clusters that collided, not a gentle brushing, a full-on cosmic crash at millions of miles per hour. And we can observe the aftermath in X-rays and in gravitational lensing simultaneously. When 2 galaxy clusters collide, the individual galaxies mostly sail right through each other because galaxies are mostly empty space and they're unlikely to collide individually. But the hot gas, the normal baryonic matter that makes up most of the visible mass of the clusters, the gas does interact. It gets stuck. It heats up. It glows in X-rays. You can see it. Now, if there were no dark matter, the mass of the cluster should be concentrated where the gas is, because the gas is most of the visible mass. Instead, the gravitational lensing shows that the mass, the real mass, has sailed through the collision and kept going. It's separated from the gas. It's in 2 separate clumps on either side, corresponding to where the 2 clusters were before the collision. The dark matter, which doesn't interact with anything except gravity, sailed right through the collision like it wasn't there, just like I told you would pass through your hand. The gas got stuck. The dark matter kept going. And the mass map shows it beautifully, unambiguously. This is not an argument anymore. This is not Zwicky's slightly eccentric calculation from the 1930s that people could dismiss. This is a picture. This is the universe, caught in the act, showing you that there are 2 kinds of matter and they behave completely differently in a collision. I find this result spectacular. I find it the kind of result that, as a physicist, makes you want to stand up and shout something inappropriate in a very quiet library. Because here's what it also tells us. Dark matter is not just some mathematical fudge factor we invented to make the numbers work. It is a physical substance. It has spatial distribution. It can be separated from ordinary matter. It moves independently. It exists. Now, let me take a slight detour here, because I believe in being honest about the alternatives. There are some physicists, smart people, careful thinkers who have proposed that maybe we don't need dark matter at all. Maybe instead, gravity behaves differently on large scales than we think. Maybe Newton and Einstein got the details a little wrong at very low accelerations. The most famous version of this is called Mond-modified Newtonian dynamics, proposed by Mordechai Milgrom in 1983. And it actually does a pretty good job of explaining galaxy rotation curves without invoking dark matter. I want to be fair to this idea, because fairness is important in science. Mond works for isolated galaxies. It really does. In that limited domain, it's quite elegant. But Mond cannot explain the bullet cluster. It cannot explain the cosmic web structure. It cannot explain the temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, which is exquisitely sensitive to the amount and distribution of matter in the early universe. When you plug the dark matter model into the equations for the cosmic microwave background, you get predictions that match observations to extraordinary precision. Mond has struggled to do the same. This doesn't mean Mond is entirely wrong. Science is not always a clean, total victory for one side. But the weight of evidence, and I mean a crushing, overwhelming, coming from every direction weight, points toward dark matter being real. It points toward something being out there that we can't see. Now, let me address the question that I know some of you have been carrying around since part 1. If dark matter passes through everything through you, through the Earth, through the detectors we build, how on earth are we supposed to detect it directly? This is the great experimental challenge of our time. Here's the hope. We don't actually know that dark matter interacts only through gravity. Gravity is the one thing we're sure about. But dark matter might also interact via what's called the weak nuclear force, very weakly, but possibly. If that's true, then extremely rarely, once in a great while, a dark matter particle might bump into an atomic nucleus. Not electromagnetically, not as obviously as a billiard ball, but a gentle nudge, a tiny little shove. A particle that interacts weakly with matter and has significant mass is called a WIMP, a weakly interacting massive particle. And physicists have been building detectors, going deep underground to shield from cosmic rays, filling tanks with noble gases or crystals of germanium, waiting with extraordinary patience for a dark matter particle to hiccup. Deep underground in South Dakota, in Italy under the Gran Sasso Mountain, in Canada, in Australia, in Japan. And so far, nothing definitive, which is either telling us something very important about the nature of dark matter, that it's not a WIMP, or telling us that we need even bigger, even more sensitive detectors. The universe is not giving up its secrets easily. But then, why would it? Where's the fun in that? WIMPs, the favorite suspect that disappeared. I want to be very precise with you right now. I want to be more precise than people usually are when they talk about dark matter, because I think vagueness does a disservice to what is actually one of the most honestly mysterious problems in all of science. When we say dark matter, we are not saying we know what it is. We are not saying it's some specific particle that we've identified and measured and classified. We are saying there is something massive, something gravitationally active, something that doesn't interact with light, and we have called this something dark matter because we needed a name for it. The name is not an explanation. This is a crucial distinction that gets lost in popular accounts of the subject. A name is not a discovery. I could tell you that every morning invisible unicorns rearrange my furniture, and I could call this phenomenon matutinal equine displacement, and now I have a very authoritative sounding label for something I know absolutely nothing about. Dark matter is better than that, significantly better, because we have strong, convergent, independent evidence that it exists and some constraints on its properties. But we do not know what it is. And this is fine. This is where we are. And acknowledging this openly is the first step toward figuring it out. So let's talk about the candidates. The lineup of suspects that physicists have assembled over the decades, each one with some theoretical motivation, each one with some experimental search ongoing. Candidate number one, WIMPs. I mentioned these briefly before. Weakly interacting massive particles. This was, for a long time, the favorite candidate. The reason is something physicists call the WIMP miracle, which sounds religious but is actually statistical. Here's the thing. If dark matter is made of particles that interact via the weak force, and if you calculate how many of them would have been produced in the hot early universe, and how many would have survived as the universe cooled, the number comes out to roughly the right amount to explain the dark matter we observe. The numbers work without any fine-tuning. This is what physicists mean by a miracle, when the answer comes out right without having to fiddle with the dials. The strong suspicion was that supersymmetry, a beautiful theoretical framework that predicts partner particles for every known particle, would provide the dark matter candidate. The lightest supersymmetric particle, perhaps a neutralino, would be stable, massive, weakly interacting, and produced in exactly the right abundance. But then the Large Hadron Collider at CERN turned on, and we searched for supersymmetric particles, and we found none of the ones we expected. The simplest supersymmetric models are, at this point, quite severely constrained. They haven't been ruled out entirely, but the versions that would have produced a convenient WIMP dark matter candidate are mostly in trouble. And the underground detectors, the beautiful experiments in South Dakota and Italy and China and Australia, have found nothing. Nothing at the masses and interaction rates that the WIMP miracle would predict. This doesn't mean WIMPs are impossible, but the experimenters have been searching with breathtaking sensitivity, and the silence is starting to say something. Actions, sterile neutrinos, and primordial black holes. Candidate number two, actions. Now here's an interesting one. Actions were not invented to explain dark matter. They were invented, proposed by Roberto Pache and Helen Quinn in 1977, and named by Frank Wilczek to solve a completely different problem in quantum chromodynamics, the theory of the strong nuclear force. The strong force has a problem. It has a parameter that theoretically could cause it to violate a symmetry called CP symmetry, the symmetry between matter and antimatter under certain operations. But experimentally, this violation is either zero or extraordinarily tiny. Why? The theory gives no reason for it to be so small. Pexy and Quinn proposed the mechanism that naturally drives this parameter to zero. And as a side effect, as a quantum mechanical consequence, this mechanism predicts a new particle, very light, very weakly interacting, the axion. And here's the beautiful accident. If the axion exists with approximately the properties predicted by the theory, there would be enough of them left over from the Big Bang to account for dark matter. Again, the numbers come out right without fine-tuning. Another miracle. Actions are very different from WIMPs. Much, much lighter. Extraordinarily weakly interacting, even more than WIMPs. You can't search for them with the same detectors. You need entirely different experimental approaches. Some groups are using strong magnetic fields to try to convert actions into detectable photons. Others are building resonant microwave cavities. The experiments are running right now. So far, no confirmed detection. But the search space is vast. Candidate number 3, sterile neutrinos. We know neutrinos exist. They're real. We've detected them. They're famously ghostly. Billions pass through your body every second from the sun, and almost none interact. We know there are 3 types: electron, muon, and tau neutrinos. Some theorists propose there might be additional neutrino species that are even more weakly interacting than the ones we know. So weakly interacting that they don't couple to the weak force at all, only to gravity. These are called sterile neutrinos. If they're heavy enough in the right mass range, sterile neutrinos could be dark matter. They would be produced in the early universe and then just hang around, barely interacting with anything, providing gravitational mass. One intriguing hint. X-ray observations of some galaxy clusters have shown a faint line at a specific energy, 3.5 keV, that doesn't correspond to any known atomic emission. Could this be sterile neutrinos decaying, occasionally emitting an X-ray photon? Some researchers got excited. Others examined the same data and saw something less conclusive. The debate continued. Candidate number 4, primordial black holes. Back to the idea that maybe dark matter isn't a new particle at all. What if it's made of black holes? Not the supermassive ones at galaxy centers, but small ones. Maybe with masses similar to the moon or to asteroids, formed in the very early universe from density fluctuations. This idea had its moment of renewed excitement in 2016, when LIGO detected gravitational waves from merging black holes of about 30 solar masses. That was heavier than expected. And some people asked, could these be primordial black holes making up the dark matter? The constraints on this idea are tight. Primordial black holes would affect the cosmic microwave background. They'd create characteristic patterns in microlensing surveys. When a black hole passes in front of a background star, the star brightens temporarily. We've run those surveys. They rule out primordial black holes as the entire answer across a wide range of masses. But there are still some mass windows, asteroid scale, roughly where the constraints are weaker. It's probably not the whole story, but it might be part of the story. Candidate number 5, something we haven't thought of. And now I get to my favorite candidate, because this is the one that keeps good physicists honest. What if it's none of the above? What if dark matter is a particle or a family of particles that nobody has even thought to write down yet? Something that requires new physics beyond what we've imagined. A whole new sector of particles interacting with each other in a dark sector, completely invisible to us except through gravity? This is not wild speculation. This is how science has worked repeatedly throughout history. Neutrinos were predicted by Pauli in 1930 and not detected until 1956. Nobody had them in any theory before that. The positron, the anti-electron, was predicted by Dirac and then found. The Higgs boson was proposed in the 1960s and discovered at CERN in 2012. Nature has particles in it that we don't know about yet. This is a fact. We have discovered new particles repeatedly. Why would we think we've found them all? The universe has 5 times as much dark matter as visible matter, and it doesn't seem particularly concerned about whether that fits into any of our models. Let me tell you about another possibility that I find delightfully strange. What if there are self-interacting dark matter particles? Particles that don't interact with us, but that do interact with each other. Their own forces, their own dark photons, their own dark chemistry. A whole parallel particle physics sector, completely inaccessible to us, coexisting with our universe in the same space, woven through everything, interacting with our world only through the one force that doesn't discriminate. Gravity. This would mean that right now, as you sit there might be entire complex processes happening around you and through you. involving particles that have as much structure and variety as our own particle zoo, and you would never know. You couldn't know. You can't look at it. You can't touch it. You can't communicate with it. Is that frightening? I suppose some people find it frightening. I find it magnificent, because it means the universe is even richer, even more layered, even more full of surprise than we thought. Every time we've looked at the universe carefully and honestly, we've found it to be bigger and stranger than we expected. Every single time, without exception. Why would dark matter be any different? Now, I do want to caution against one thing. I've seen the headlines. Scientists close to solving dark matter mystery. New experiment may reveal dark matter within 5 years. I've been reading headlines like this for 30 years. The mystery is still here. The particle is still undetected. I'm not saying we won't find it. I'm not being pessimistic. I genuinely believe that if we keep building better experiments, keep asking better questions, keep refining our theoretical frameworks, we will eventually figure out what dark matter is. But I also think we should be humble about the timeline. Nature does not owe us answers on a schedule that's convenient for our grant cycles or our careers or our impatience. Sometimes the most important problems take a long time. The good ones are worth it. Dark matter is blowing through you right now. I want to talk to you about something a little more personal now, a little more immediate, because so far I've been gesturing at things that are enormous galaxy clusters, cosmic webs, the large-scale structure of the universe. And I think it's easy to hear all of that and feel like it's very far away from you, very abstract. It isn't. Let me tell you what is happening to you right now, in this moment, as you exist. The Milky Way is sitting inside a dark matter halo, a vast, diffuse cloud of dark matter particles enveloping our entire galaxy, extending for hundreds of thousands of light years. This cloud is not static. It moves. It flows. It has a kind of weather at cosmic scales. And the solar system is moving through this cloud. Our solar system orbits the center of the galaxy at about 220 kilometers per second. Every second, we're moving 220 kilometers through space, through the dark matter halo, which means the dark matter isn't just sitting there around us from our perspective, it's sweeping through us. A wind, a dark matter wind, blowing through the earth, through every building, through every person. The numbers are not small. Current best estimates suggest that there are roughly 300 to 600 million solar masses of dark matter in every cubic kiloparsec of our galactic neighborhood. A kiloparsec is about 3,260 light years. If you scale that down to the scale of, say, a classroom, well, it gets very small very quickly because the density is spread over an astronomical volume. In any given cubic centimeter near Earth, you'd expect something like a fraction of a proton mass worth of dark matter. Very diffuse. But here's the thing. A proton mass is very small, and dark matter particles are thought to be many orders of magnitude heavier than a proton, anywhere from a few proton masses to millions of times heavier, depending on the model, which means if they're heavy particles, there are fewer of them, but each one packs more mass. If they're very light, like axions, there are astronomical numbers of them in every cubic centimeter. Billions upon billions of axions, if that's what dark matter is, passing through every cubic centimeter of space, including through you, right now, at all times. This is not science fiction. This is what our best current understanding of the universe implies. You are literally made because of dark matter. Now, let me take this further, because I think the history of how we got here into this galaxy, into this solar system, is inseparable from dark matter in a way that most people don't appreciate. I mentioned earlier that dark matter formed the scaffolding for the first galaxies. Let me be more specific about our galaxy and our solar system story. About 13.6 billion years ago, a region of the dark matter halo that would eventually become our galaxy started to collapse under gravity. The dark matter concentrated first, forming a potential, well, an invisible gravitational bowl, and then the ordinary matter fell in. Hydrogen and helium, the stuff of the Big Bang, flowing into the preformed dark matter structure. That matter swirled, collapsed, fragmented, and lit up. The first stars in the Milky Way formed inside a dark matter halo. Generations of stars lived and died, exploding as supernovae, seeding space with heavier elements, the carbon and oxygen and iron that would eventually end up in you and me. All of this happened inside a dark matter halo that provided the gravitational structure to hold the galaxy together. Our sun formed about 4.6 billion years ago in a collapsing cloud of gas and dust, a cloud that was already enriched by the products of multiple stellar generations. That cloud was held in the galaxy by gravity, some of it from visible matter, much of it from the invisible halo. The Earth formed from the leftovers of the sun's formation. Every atom in your body, the carbon in your DNA, the oxygen in your lungs, the calcium in your bones, the iron in your blood, every one of those atoms has a history that goes back billions of years through stellar explosions and molecular clouds and the formation of this solar system. And all of that happened in a galaxy held together, shaped, and given its structure by dark matter. In a very deep sense, you are a product of dark matter. Not because dark matter made you directly, it has nothing to do with the chemistry or biology of your existence. But the stage on which your existence became possible was set by dark matter. Remove the dark matter from the universe, and you don't just remove some invisible background mass. You remove the structure that allowed galaxies to form, that allowed stars to coalesce, that allowed the elements of life to be forged and distributed. You remove the possibility of us. I find that extraordinary. I find it one of the most humbling thoughts in all of science. We owe our existence, in some fundamental cosmic sense, to something we have never seen and do not understand. Now, let me also tell you about something that is happening on an even more intimate scale. Something that, if you're experimentally inclined, you might want to do something about. Right now, at this very second, every square centimeter of your body is being traversed by an enormous number of neutrinos from the Sunday trillions per second, to the top of your head, to your brain, to your chest, out the bottom of your feet. You don't feel it. There's no sensation. Your body is essentially transparent to them. Dark matter particles, if they exist in the forms we think, are doing something very similar. The numbers are smaller, far fewer particles per second, because dark matter is less densely packed than the solar neutrino flux near Earth. But they're passing through too. And unlike neutrinos, which we've measured, which we know the mass of approximately, which we've caught in giant tanks of water deep underground and watched produce a little flash of light occasionally, unlike neutrinos, the dark matter particles have never been caught, not once. This represents, I think, one of the most fascinating and humbling failures in the history of experimental physics. Not a failure of effort, we've tried enormously hard. Not a failure of cleverness, the experiments are marvels of ingenuity. But a failure to find what we confidently expected to find. The LUX Zeppelin experiment in South Dakota. 10 tons of liquid xenon, a mile underground, looking for the faint nuclear recoil that would indicate a WIMP hitting a xenon nucleus. The results, nothing. Constraints on the WIMP interaction rate that are so tight they rule out vast swaths of theoretical parameter space. The Panda X experiment in China. Similar technology, similar result. Xenon 1T. Now Xenon in Italy. Again, constraints tightening, nothing detected. The experiments are not wrong. They're working. They're sensitive. They have detected things once. Xenon found a faint, unexplained excess of events that caused considerable excitement, which turned out to be trace radioactive contamination. Science working as it should. Get excited. Check carefully. Find the mundane explanation. What the null results mean, the great void of non-detection, is complex. Either the WIMP doesn't exist in the mass range we searched, or it interacts more weakly than our models predict, or it's a different kind of particle entirely. The search is shifting. More attention to lighter particles, sub-GeV mass dark matter, which would produce recoils too small for traditional detectors to see, requiring entirely new detection strategies. More attention to axions, more attention to dark photons, more attention to possibilities we hadn't fully considered before. Science pivots. This is what science does. You try the obvious thing first. The obvious thing doesn't work. You think harder. You try less obvious things. This is not failure. This is the process. Let me also tell you about something that haunts me a little, and I don't use the word haunted lightly because physicists are not typically the haunted type. We have what's called the hierarchy problem in particle physics. The mass of the Higgs boson, the particle responsible for giving mass to other particles, is much lighter than you'd expect based on quantum corrections. These corrections should, according to the theory, be astronomically large, pushing the Higgs mass up to the Planck scale. They're not. The Higgs is light. This requires an extraordinary fine-tuning of parameters that has no natural explanation in the standard model. Supersymmetry would solve this problem, and supersymmetry, as I mentioned, would provide WIMP dark matter candidates. The LHC didn't find supersymmetry in the expected place. This leaves us in an uncomfortable position. Either supersymmetry exists but is much heavier than expected, making it less natural, or there's some other solution to the hierarchy problem we haven't found yet. Or maybe the hierarchy problem isn't actually as bad as it looks. Maybe there's some anthropic argument, some multiverse reasoning that makes the fine-tuning acceptable. I have limited patience for anthropic arguments personally. They feel like giving up. They feel like saying the universe is the way it is because otherwise we wouldn't be here to notice, which is true, I suppose, but it's not the kind of answer that gets you anywhere. But more relevant for our purposes, the elegant alignment between the solution to the hierarchy problem and the dark matter problem, the WIMP miracle, as I called it, may be illusory, may be a coincidence, may be the universe dangling a beautiful numerical accident in front of us to distract us from the real answer. The universe has done this before. The universe is not above misleading us. And so we search, and so we think, and so we ask new questions, and devise new experiments, and argue about interpretation, and occasionally get very excited about a signal that turns out to be background noise, and occasionally get deeply frustrated. And always, always come back to the central, unavoidable fact. There is something out there we don't understand. Something enormous, something everywhere. Something that helped build everything we love about the universe, including ourselves. And we don't know what it is. The universe's baby photo and what it reveals. Let me tell you about the cosmic microwave background radiation, because I think it is, in a very real sense, the Rosetta Stone of modern cosmology. And it has a great deal to say about dark matter. In the beginning, and I love talking about the beginning, because it makes me feel both very small and very excited simultaneously. In the beginning, the universe was hot, unimaginably hot, so hot that atoms couldn't exist. Protons and electrons flew around separately, and the whole universe was a kind of plasma, an ionized fog. Light couldn't travel through this fog. Every photon immediately scattered off a free electron. The universe was opaque. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This is called recombination, which is a slightly misleading name since they'd never been combined before. But physicists are not always the best at naming things. I'll put my hand up on that. When this happened, the universe became transparent for the first time. The light that was everywhere trapped in the plasma suddenly could travel freely. It scattered for the last time and then streamed outward. That light is still traveling today. We can detect it. It's microwave radiation coming from every direction in the sky with almost perfect uniformity. Almost. Not quite. There are tiny temperature fluctuations, 1 part in 100,000 imprinted in it. These fluctuations are the fingerprints of the early universe. And they tell us, with extraordinary precision, how much dark matter there is. Here's the physics. Before recombination, the universe was full of acoustic waves, pressure waves, traveling through the plasma, like sound waves in air, but at cosmic scale. The dark matter, which doesn't interact with light or with the plasma pressure waves, just sits there, gravitationally. But it shapes the gravitational landscape. It affects how the acoustic waves behave. The pattern of temperature fluctuations we see in the cosmic microwave background is the result of these acoustic oscillations, frozen at the moment of recombination. By measuring the pattern, the angular power spectrum, as we call it, we can read off the composition of the universe. And what we find is 27% dark matter, 5% ordinary matter, 68% something even more mysterious that we're calling dark energy, which is driving the accelerated expansion of the universe, but which is a separate story for another time. 27%, not 5%, not 50%, 27%, and 5% for us. These numbers come from an independent measurement, completely different from galaxy rotation curves, completely different from gravitational lensing, completely different from the bullet cluster, and they're all consistent. The consistency should hit you. It's not one observation that we might be misinterpreting. It's a dozen independent observations using completely different physics, different instruments, different mathematical frameworks, all pointing to the same answer. This is how science builds confidence, not through a single dramatic discovery, but through convergence from multiple directions, fuzzy dark matter and the Hubble crisis. Now let me tell you about something that makes even cosmologists a little uneasy. The tension in cosmology, there's a quantity called the Hubble constant, the rate at which the universe is expanding. You can measure it two ways. You can measure it locally, look at supernovae in nearby galaxies, calibrate their distances, compare distances to recession velocities. Or you can measure it from the cosmic microwave background, extrapolate the expansion from the early universe to today using our cosmological model. Both measurements are now precise. Both measurements disagree with each other. Not by a lot, a few percent, but enough that it's statistically troubling. This is called the Hubble tension, and it may just be systematic measurement errors. Or it may be telling us that our cosmological model is missing something. Some new physics, maybe something about dark matter itself. There are theorists proposing early dark energy, some component of energy in the early universe that dissipated before recombination and isn't there today. Others are looking at more exotic dark matter models. Nobody knows the answer. And this is what the frontier of science looks like. Not a clean, finished picture. A picture with tensions in it, anomalies, data points that don't quite fit. These are the cracks through which new understanding eventually pours. I want to tell you something about the nature of not knowing, because I think our culture has a complicated relationship with ignorance. We're taught that ignorance is bad. We celebrate knowledge, expertise, certainty. The worst thing you can say in a public forum is, "I don't know." But in science, "I don't know" is the most important sentence there is. It is the engine of progress. Every important discovery in the history of science began with someone who was honest enough to say, "I don't know, and I find that unacceptable, so I'm going to do something about it." I don't know. The most powerful words in science. We don't know what dark matter is. I don't know what dark matter is, and I find that absolutely wonderful, and I find it absolutely unacceptable, and those two feelings exist simultaneously without contradiction. Wonderful, because it means the universe is still surprising us. After 400 years of increasingly powerful physics, there is something that makes up 27% of the energy content of the universe, and we haven't the faintest idea what it is at the particle level. The universe is genuinely strange. It has not become boring. Unacceptable, because we should figure it out. We have the tools, maybe not quite the right tools yet, but we can build better ones. We have the mathematical framework, quantum field theory, general relativity, that has been spectacularly successful at everything else. We have the drive, the curiosity, the sheer stubbornness that has characterized the best of human inquiry. We should figure it out. Now let me tell you about some of the more speculative but intellectually tantalizing ideas at the frontier. There's a concept called fuzzy dark matter. If dark matter is made of extremely light bosons particles with a very small mass, perhaps 10 to the power of minus 22 electron volts, which is almost unimaginably small, then the quantum mechanical wave nature of these particles becomes important at astrophysical scales. In quantum mechanics, particles behave like waves. For ordinary particles, this quantum wave behavior is important at tiny scales, atomic scales. But for particles with extremely small mass, the quantum wavelength, the de Broglie wavelength, can be enormously larger. For particles with this ultralight mass, the quantum wavelength would be on the order of a kiloparsec, thousands of light years. What this means is that the dark matter wouldn't be a bunch of discrete particles, but a coherent quantum wave filling the galaxy. The density would have a smooth, wave-like character rather than the granular, corpuscular character of heavier WIMPs. This matters because one of the tensions between standard dark matter theory and observations concerns the density profile at the center of galaxies. The simplest models predict a sharp cusp, a spike of density at the galactic center. Observations often suggest a flatter core. Fuzzy dark matter, with its quantum pressure at large scales, naturally produces cores rather than cusps. Is this the answer? We don't know. It's a fascinating idea that's genuinely consistent with some observations and has difficulty with others. There's also the concept of self-interacting dark matter, or hidden dark matter particles that have a force between themselves. Not like electromagnetism, which acts between opposite charges over long ranges. Something more like a contact interaction, or mediated by a dark photon that only dark matter couples to. Why would this help? Because self-interactions would allow dark matter to redistribute itself within halos. Energy would be transferred between particles, the way molecules in a gas exchange energy through collisions. This would smooth out the cusps in galactic centers, bring the theory into better agreement with observations of dwarf galaxies and galaxy clusters. The models are being tested. The data is being analyzed. Science proceeds. And then there's the question of the earliest universe. We know that dark matter was present during Big Bang nucleosynthesis, the period when protons and neutrons combined to form the light elements, hydrogen, helium, lithium. The amount of dark matter is inferred from the cosmic microwave background. But what was dark matter doing before recombination? The particles were present. They were moving. If they were warm enough in the right kinetic energy range, they would have been freely streaming, smoothing out small-scale density fluctuations. The mass of the dark matter particle determines whether it's cold, slow-moving, preserving small-scale structure, or warm, faster, washing out small-scale structure. Cold dark matter, the standard model, works very well on large scales. It predicts the cosmic web. It predicts the number of massive galaxy clusters. But at small scales, below the scale of dwarf galaxies, there are discrepancies. There appear to be fewer dwarf galaxies around the Milky Way than cold dark matter simulations predict. There appear to be fewer dense satellite galaxies than expected. Are these discrepancies fundamental, telling us that dark matter is warm, or self-interacting, or something other than cold? Or are they the result of complicated baryonic physics, supernova explosions blowing matter out of small galaxies, reionization stripping gas from dwarfs that our simulations don't capture correctly? Both. Probably both. The question is, which effect dominates? These small-scale structure problems are one of the most active areas of debate in modern cosmology. Very smart people disagree about the interpretation. This is science doing what science should do, arguing carefully about what the data means, designing new observations to discriminate between models, being honest about uncertainty. Let me tell you about one more line of investigation that I find particularly beautiful: strong gravitational lensing, specifically the technique of gravitational microlensing used to search for compact dark matter objects. If dark matter is made of black holes or other compact objects passing through the galaxy, they would occasionally pass directly in front of background stars. When they do, their gravity acts as a lens, momentarily brightening the star in a very specific, characteristic way. The duration of the brightening tells you the mass of the lensing object. We've run enormous surveys, watching millions of stars in the Magellanic Clouds, watching stars in the galactic bulge, and carefully cataloging every brightening event. We've found microlensing events, but far fewer than you'd expect if the dark matter halo were made of compact objects in certain mass ranges. And so the possibility of planet mass or stellar mass compact objects making up dark matter is essentially ruled out. The window for primordial black holes is small, as I mentioned earlier. The data is telling us something. Not yet what it is, but many things that it isn't. And eliminating possibilities is progress. It might not feel like progress. It might feel like failure. But every time an experiment rules out a model, the space of remaining possibilities shrinks, and the eventual answer comes closer. The beautiful, terrifying, unfinished universe. I've been taking you on a journey through galaxies and clusters, through particles and waves, through experiments and their silences, through the history of a mystery that has grown larger the harder we've looked at it. I want to end by talking about what this all means. Not in a mystical sense, I don't go in for mysticism, but in a genuine, intellectual, honest sense. What does it mean for us, for human beings, for science, for our picture of reality, that 27% of the universe is made of something we cannot identify? Let me start with what I believe is the most important lesson. Darkness, genuine, fundamental darkness, not just the absence of light, but the absence of interaction, is a real thing in the universe. Not a metaphor, not a philosophical concept, an actual physical category. There are substances in nature that are present, that have mass and gravity, that shape the universe we live in, that are passing through you right now, and that are constitutionally, fundamentally undetectable by any of your senses or any instrument that exploits the electromagnetic force. We have spent all of human history building knowledge from what we can see, touch, hear, smell, taste. Our instruments are extraordinary extensions of these senses: telescopes to see farther, microscopes to see smaller, spectroscopes to analyze light, particle detectors to catch the invisible. All of these instruments, all of them work through the electromagnetic interaction. They detect things because those things interact with photons or with the electrons in our detectors. Dark matter cannot be detected this way. We are blind to it, the way a bat equipped only with sonar is blind to starlight. Not because the starlight isn't there, but because the bat's sensory apparatus doesn't couple to it. We built our entire sensory apparatus, biological and instrumental, around one of the four fundamental forces. And nature, indifferent as always to our convenience, put most of the matter in the universe in a category that our favorite force can't touch. This is, I think, profoundly humbling. Not in a depressing way, in a useful way, because it corrects a bias that is easy to fall into, especially in a technological civilization that has achieved such spectacular success through electromagnetism. The bias is that the universe is, at its core, something we can in principle grasp that with enough instruments, enough cleverness, we can see everything. We cannot see everything. Most of everything is invisible to us by fundamental principles. Now, I want to push back against the possible response to this, which is despair. We can never know the universe. It's all hopeless. Science has limits. This is wrong, and I'll tell you why. We found dark matter through gravity. We don't understand it, but we found it. We found it by being clever about what gravitational effects we could measure. We have mapped its distribution across the universe. We have constrained its properties. It must be non-relativistic, moving slowly. It must be non-baryonic. It must have formed before the universe was transparent. It must be stable on cosmological timescales, or nearly so. It must cluster on galactic scales. We know a great deal about it without having directly detected a single particle. And the search for that direct detection is the most aggressive, creative, expensive, experimental program in physics today. New detectors are being built. New theoretical ideas are being explored. New observational techniques are being developed. Gravity waves from merging dark matter substructure, precise measurements of the shape of dark matter halos, the distribution of the smallest dwarf galaxies, hints from high-energy cosmic rays, gamma rays from galactic centers, X-ray lines in galaxy clusters. The net is being cast in every direction. One of these experiments, I can't tell you which one, because I genuinely don't know, and anyone who tells you they know is overconfident. One of these experiments, or an experiment we haven't designed yet, will find something. A signal, an anomaly, a deviation from background. And that signal will be the first direct evidence of a specific dark matter particle. When that happens, and I say when, not if, because I believe we will figure this out, when that happens, it will be one of the greatest moments in the history of science. Not just because we'll finally know what dark matter is, but because we will have crossed a boundary. We will have, for the first time, directly detected something from the dark sector of the universe. Something that doesn't interact with light. Something whose existence we inferred entirely from its gravitational effects. It will be like hearing a new note that the universe has been playing all along, inaudible to us, and suddenly our instruments become sensitive enough to catch it. I want to take a moment to talk about what comes after that discovery, because I think it might be even more extraordinary. If there is dark matter, and it interacts via some force, even a tiny, subtle force, then there might be dark chemistry, dark atom equivalents, dark molecules, even. There might be a whole structural richness to the dark sector that we can't imagine yet, because we've only ever known one kind of matter in its chemistry. This is very speculative, but not impossible. And science at the frontier has to allow itself to imagine the possible. In the early days of atomic physics, we thought atoms were the indivisible building blocks of matter. Electrons, protons. Then we found the neutron. Then we found that protons and neutrons were made of quarks. Then we found gluons and the structure of the strong force. Then we found the W and Z bosons and the electroweak force. Then we found the Higgs. Every layer we peeled back has revealed more richness, more complexity, more structure than the layer before. Why should the dark sector be simpler than the visible sector? There's no reason. Physics, as far as we can tell, doesn't prefer simplicity. It allows it sometimes, but it certainly doesn't require it. The dark sector might be a whole new physics, as rich as the standard model, sitting alongside our universe in the same space, communicating with us only through gravity, waiting to be understood. Or it might be simple, a single particle produced simply, interacting simply, stable forever. A boring answer that is nonetheless the right one. We don't know yet. And here, at the end, I want to say something that I feel very strongly about, something that I've believed my whole career and become more convinced of with every passing year. The universe is not obligated to make sense to us. This sounds pessimistic. It isn't. Let me explain what I mean. The universe did not evolve so that human beings could understand it. We evolved to survive on the African savanna, to hunt prey, avoid predators, find mates, raise children. The cognitive machinery in your skull was selected for those tasks. It was not selected for doing quantum field theory or understanding the large-scale structure of the cosmos. The remarkable, beautiful, improbable fact is that our brains, despite being built for savanna survival, can do physics, can reach out into the structure of reality and find, time after time, deep mathematical relationships that are true, can predict the behavior of particles at energies never seen in nature and be confirmed by experiment to extraordinary precision, can, from the orbits of stars in distant galaxies, infer the existence and abundance of an invisible form of matter. This works. It actually works. And I think about that sometimes, and I feel a kind of wonder that I don't quite have words for. But the fact that it works so well in so many domains should not convince us that we've seen everything, or that the universe will be kind enough to present itself in a form that fits our current conceptual framework. Dark matter is, I think, a gentle reminder from nature, a reminder that we are still at the beginning, that the 5% of the universe we understand in detail is not the whole story, but a footnote in a story whose bulk we can barely read. And I love this reminder. I love that the universe still has the capacity to humble us. I love that after centuries of science, after Newton and Maxwell and Einstein and Bohr and Feynman and all the rest of us, after all of that nature can still look us in the eye and say, you haven't figured me out yet. Keep trying. Keep trying. There is a kind of person, and I have met them, and they exist in every field, who is made uncomfortable by uncertainty. Who wants finished answers? Who wants a textbook, a final version, a complete picture? Who feels anxious when the frontier is fuzzy and the leading theories are contested? I understand the desire. Uncertainty is uncomfortable. The human mind craves resolution. But uncertainty is where the action is. Uncertainty is where discovery lives. Every single thing that is now in the textbooks, every settled piece of science, was once a controversy, a puzzlement, an anomaly that didn't fit. It only looks inevitable in retrospect. Dark matter is in the uncertainty phase right now. It is exactly at that stage where the evidence is overwhelming and the explanation is unknown. This is the most exciting place in science to stand. It is the exact place where new physics enters the picture. There are young physicists right now who will spend their careers on this problem. Some of them are reading papers about axion detection. Some are designing next-generation liquid xenon detectors. Some are writing code to simulate dark matter structure in the early universe. Some are working on telescopes that will map the cosmic web with unprecedented resolution. Some of them will be part of the team that figures this out. That measures the dark matter particle's mass, its spin, its interaction strength. That finally puts a name, a real name, not just dark matter, to the ghost that's been passing through us all our lives. When that happens, and it will happen, the picture will change. Our textbooks will change. Our understanding of what matter is, of what the universe is made of our own place in the cosmic structure, all of it will shift. And then the new picture will have its own anomalies, its own unexplained edges, its own hints of something deeper, because that's how it works. That's always how it works. And that is not a bug. That is the most beautiful feature of our relationship with nature. We ask questions. The universe answers. The answer reveals new questions. And on, layer after layer, mystery after mystery, wonder after wonder, until the asking itself becomes a kind of joy. The joy of finding things out. Dark matter is everywhere around you. It's been there since before the earth existed, since before the sun was born, since the universe was a few 100,000 years old and just becoming transparent for the first time. It weighed on the structure of the cosmos when the first stars lit up. It held the Milky Way together while the chemistry of life was being invented, atom by heavy atom, in the hearts of massive stars. It's in this room with you. It's passing through you. It doesn't know you exist. And in a sense, until 60 years ago, you didn't know it existed either. Now you do. What you do with that knowledge, how you sit with that mystery, how it changes your sense of your place in the universe, whether it makes you feel small or vast or both. Simultaneously, that's up to you. But my recommendation, for what it's worth, is this. Let it astonish you. Because the universe, strange and dark and mostly invisible, containing things we've never seen and forces we're only beginning to imagine, is genuinely, spectacularly, almost unbearably interesting. And isn't that enough